Go live. Ready? We are live. All right. Hello, everyone. Welcome to today's brand new episode of Corecast. I am your host, Tim.
And this is Sahil. Welcome, everybody, to a brand new, exciting episode of Quirkcast. If you are on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions in the episode so we can get to them. And if you haven't joined our Discord channel, please do that so you can ask us questions there. So, without further ado, let's get to it. So, I guess Tim, although in amendments, I will say that we did take a hiatus last week, so may not be every Tuesday, but what we aspire to. Yeah. So, given that we've taken a little bit of time, we were thinking about centering this next series of episodes around the notion of time. But wanted to start off by discussing something that may seem orthogonal to that, but can potentially be related, as we'll find out in this episode. Maybe, maybe not. So, Tim, I was listening to several podcasts by like well-respected, physics professors and whatnot, and or physics professors being guests, and they talk about like the notion of like how the universe started off and then, got to where we are, how it started off in what they call a low entropy
Mm-hmm.
state. And I thought that might be an interesting thing to like unpack, kind of like why is this question so difficult? Like what's the deal with this question? Like why did the universe start off in the state that it's in? And typically people are used to the notion of entropy
Mm-hmm.
being a measure of disorder and chaos, like, and that the universe tends to want to
Mm-hmm.
increase its entropy. And so I want to like kind of go through that, a line by line and kind of dissect that. So let's start off with like what is entropy? Maybe you can start off with like what people think entropy is and like what it actually is, if they match or if they don't match.
Yeah. Let me preface just say that there's almost a little bit of discrepancy, right? So when people talk about time, they're very interested in the era of time. That time seems to flow only one way. We go from the past to the future, and whenever you see a movie goes forward, and if you play the movie backward, it looks very awkward, right? Like you can drop a plate on the floor, it breaks, but if you play it backward, the plate kind of just unbreak itself. It will look really weird. So we see that it seems like there's certain level of difference between the past and the future, but yet the discrepancy in physics is that the physical law actually does not have this discrepancy. A lot of physical laws that we have looks the same forward and backward. Now, this is sort of where entropy comes in, and so physics has developed a whole suite of approximations that goes into the realms of statistical physics and all that. And there's this entropy. It's a rather technical concept that comes up, and as a result, people a lot of times when people ask the question, well, how come there's an error of time? People kind of just blame it on the entropy now. It's like, oh, entropy increased, and that causes the error of time. But it's actually not really an explanation because you're kind of just shifting the blame from one concept to another. And now, and now, because of this, there is a lot of mystery regarding this concept of entropy. It's kind of like, oh, it's just the way the universe is. It captures some of the essence of why time moves forward, and as a result, because we see things kind of tend to break, right? Then there's this notion that, oh, maybe it's kind of like some kind of disorder, chaos behavior associating with this entropy. But actually, there is a very technical definition. And it turns out the entropy is kind of anything but a measure of disorder. So it's quite far from that.
Oh, that's very strange because whenever I saw like a web comic by XKCD that's like, don't teach your kids about entropy because they leave the room disorganized and you just say, oh, entropy is going up. So I guess like if you're saying entropy is not a measure of like chaos and disorder,
Mm,
like what is it? That really flies in the face of a lot of very common like things. I mean, like if I, just before you answer, like as an example, like if I were to, separate, if I were to keep a hot object by itself and a cold object by itself and then bring them in contact with each other, they tend to go into thermal equilibrium, which increases entropy, at least
Mm-hmm.
based on what I
Mm-hmm.
had learned. So and I would assume that like it's more, I guess, I don't know if more disorder applies, but like how does that work? And getting to your definition of entropy, and can you give examples of like how people typically explain it, and then in this new
Mm-hmm.
light what it is? That might be very helpful to our audience.
Yeah, yeah. So there's a tiny bit of math involved, but at its core, entropy is a counting exercise. It's counting the number of possibilities. So, for example, if I have a coin, and a coin can go head or it can land heads or tails. For that, those two specific configurations, we can say there is two possible configuration. And when you calculate the entropy, there's some formula, mathematical formula involved. You can convert the number of configuration. Technically, you take the logarithm multiplied by some constant, then you get some unit of entropy, right? But
Well, just one point I want to add to that is that to say how it's related to number of configurations, could you say like it's the number of yes no questions that you need to ask to get like what the configuration of the system is?
yeah, roughly in some specific
Okay,
units, it's proportional to
okay,
that, right? So
got it.
it's easier for our discussion to just look at the number of possibilities. So because the more number of possibilities, the higher the entropy, the fewer the lower the entropy, right? So this definition actually very simple, right? If for example you look at a coin, it's got two, so entropy is it's computed from two possibilities. You look at a die, it's got six possibility, then entropy is related to that. And then of course the next question is, well, where do these concept about disorder comes from? I mean, there seems to be some relationship, right? But the so far the link is a little missing. There is a little bit missing there.
Mm. So actually, okay, one example I've seen, the hot cold example may have not been the most apt, but like imagine I have this like finite box and I have a bunch of like particles, like a large number of particles, and I confine them to one corner, one tiny corner of the box, and just
Mm-hmm.
ignore charge and stuff. Assume they're neutral and they're billiard balls bouncing. If I were to like release those like small like I guess barriers that keep them confined in that corner, they'll spread apart throughout the entire room.
Mm-hmm.
And so it's like there is more disorder because they're all over the place. So how can you tell me it's not disorder?
Yeah, and the one thing I would say that disorder to some extent is kind of in the eye of the beholder, right?
Mm,
Imagine you're an artist, right? Let's say somehow you get hold of five different air molecules. Maybe in one art pieces you hide all those air molecules at a corner. That's one configuration. But then
mm,
maybe an hour later you can arrange these molecules in the shape of a dragon. I don't know. Certainly it has spread out into the room, but it's still one possibility because it's very intentional, right?
mm,
And the artist is kind of an analogy to physics, right? You can think of physical law. It's kind of like an artist. It's trying to place these air molecules in a very specific configurations. So from that lens, if you kind of pretending like, oh, you kind of keep track of all the particles and the way they move, you can kind of argue that, look, the air molecules only has one possible configuration. Like it wouldn't have been any other way. So if you think from that perspective, the number of configuration really has not changed. It's the same before and after, right?
mm. But hold on a sec. I mean, it's occupying a greater volume. So I don't understand like how it can be
Mm-hmm.
a same configuration because it has more possibilities to explore versus being artificially confined in like, in the small volume. But if it's a larger volume, clearly has more possibilities. So entropy
Exact,
goes up. What gives?
exactly. The key, I think, is possibility, right?
Okay.
Because if we see the configuration of air molecules in a room,
Mm,
nature only has one possibility because that's just the
mm,
way it is. But to us humans, we see
mm,
particles in a box. We notice that there could be many, many different possibility, and for us humans, we can't distinguish them, right? Like if an artist, I don't know, let's say an abstract artist plays 1,000 air molecules in some configuration, if to the untrained eye you can move any one of them and it will look kind of the same, right?
Mm-hmm.
So really, the crux of the definition of entropy lies in, well, what are you counting? We're really counting the possibilities given our ignorance, because we're ignorant. Well, we don't know what the details of the artistry is, right? So
Mm-hmm.
we look at the configuration at face value, but like, oh, okay, the only thing that we care about is the volume of the box. So of course, any configuration could be plausible because we don't
Mm-hmm.
keep track of the air molecules. So even though the volume is larger, right, the reality is that there isn't more possibility, but there is more apparent possibility, right? So this is
Mm.
what entropy really is about. Is given the amount of it's almost like information, right? Given the things that we can observe,
Mm-hmm.
how much can we narrow down the possibilities, right? If you have a bigger box, well, it's harder to narrow down those possibilities. So it kind of has more to do with us, kind of like how much unknown do we anticipate, basically.
Yeah, so I guess one question that could come up is like we have let's say the world was classical, like forget about quantum mechanics
Mm-hmm.
because we're arguing classically so far. We have exact laws of how things move, like gravitational laws and all that stuff. Like why does like this uncertainty still come up is my question. Can you delve a little bit into that, even in classical physics?
Yeah, the problem is when we're trying to count possibilities, you have to first ask, well, what are you counting, right?
Hmm.
In like in classical physics, a particle is infinitesimally small, right?
Hmm.
So if I draw a dot in a box, well, how many dots can I draw really? Like that's roughly the number of possibilities, right? So when you
Hmm.
do that, the number is actually infinite, right? It doesn't matter how big or small my box is. There are infinitely many dots I can draw. I mean, it would just be a little
Yeah.
less dense, but it still is infinite. So
Hmm.
in that sense, you can't really define entropy, right? Because the only answer you're gonna get is infinite. Maybe you go from one infinity to another infinity, and there are all these paradoxes with infinity. Like, is one infinity larger than another infinity? Like, this becomes very ambiguous. So, so now you can see like entropy kind of has a level of ambiguity, right? Like, you kind of cannot count possibilities if each particle is infinitesimally small. You kind of have to put them in, like slightly larger boxes than infinitesimal, basically.
I see. Okay, what if I were to make like each like particle like a finite size rather than infinitesimal? Would entropy still not be as well defined, or
Yeah, I mean
like?
then it will be well defined. For example, if you take a picture of the room, like a
Mhm.
microscopic picture, then you see pixels, right? Then it's like, okay,
Yeah.
then the particle could be in this pixel, in that pixel, blah yada yada yada, right?
Mhm.
But then now well, in order to define entropy, you have to artificially introduce this concept of a pixel, right? Nature doesn't have a pixel. It's a pixel
Mhm.
that we impose on realities. It's to help us keep track of things, right?
Mhm.
And once you put this pixelation in, then kind of all hell's break loose. Then you see that, oh,
Mhm.
entropy has these strange properties that it seems to increase over time and whatnot. But if you look at where that comes from, ultimately it is artificially because of the way we define it. We're confining it to pixel, of course. Then it will try to explore the different pixels over time.
Mm. I see. I see. So could you say that entropy is not well defined because then there's a question of like if you go with this pixelated approach, how big each pixel you make, and that'll change the entropy?
Exactly. Yeah. And
Mm.
exactly that's the problem. So in a sense, if you don't have this pixelation, and entropy isn't really well defined. There's only one configuration, or infinitely many configuration, right? Like either way, it's not a very interesting answer. But once you put a pixel grid on, then you notice that, hey, look, entropy seems to kind of increase in that way. But it's just a testament that the nature doesn't like to conform to the way we pixelate things. Because nature doesn't know, right? Like the laws of physics doesn't know that we somehow put a pixel grid on it. It doesn't know that, right? So of course particles would not respect that, right? Like if you put all the original particles in one pixel, there's no reason for them to continue to do that. That's why it would try to spread out. So the increase of entropy it's almost kind of like, like if you try to pixelate things in the way that nature doesn't care, nature is not going to respect you either. So in that way, it's kind of like it's not so mysterious anymore if you see it that way.
Is it kind of like human behavior if you were to like put let's say like very strict conditions, people will want to like not respect those in some sense.
Yeah, I guess it's kind of like that. If you have too many rules, nature is
Yeah.
like a rowdy kid. Be like, oh, why do I have to listen to you? I do my thing, right? I,
Yeah.
actually, there's a very good analogy.
Okay.
A very good analogy is to look at the digits of pi. I don't know how many digits you remember, right? I remember quite a few. Maybe like it's 3.14159265359, something like that. Don't quote me with
That's
that.
way more than me. I remember 3.14159. That's it.
Right. And some people could remember to a million to a million digits, right? Okay.
Yeah.
But
Yeah.
but imagine this, Sahil. Imagine you don't know anything about pi, right? And I just give you these digits: 3141596, yada yada yada, so on and so forth, right?
Yeah. Yeah. Yeah.
I mean, what would your impression be? You don't know it's the digits of pi. You just be like, just a bunch of random numbers, right?
Yeah. I would.
Yeah, and if you compute the entropy for these digits, you see many possibility. Who cares if it's 3.131419? It could have been like 1567834, whatever, right?
Yeah. Yeah.
It would have been the same to you, right? But then the moment I tell you, hey, look, dude, it's the digits of pi, you'll be like, oh man, you got me, right? So that's kind of like that. Like if you look at the digits of pi, you might prescribe that it has a lot of entropy because it's just all look random, right? But if I tell you it is the digits of pi, it's not so random anymore. But at the same time, if you look at 1 million digits of pi, you see that each digit 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 roughly appear 10% of the time, right? And you can say as well, why is that? Why is statistics so good for the digits of pi, even though, all this is kind of nonsense because there is only one pi? Well, the reason is because there's no reason for pi, for the value of pi to respect our numerical digit system, right? Why does it have to be, based on base 10, right? It doesn't respect that. So of course it's gonna try to go through most of them. There's no bias whatsoever. Why pi would have to, why the digits of pi would have to have more sevens than 5? Like why would it? Because it doesn't respect, our way of looking at numbers, right? So
Yeah.
so I would say entropy is kind of this statement that I mean, like you said, it's like a rowdy kid, it does not like to be respecting the regularity we impose on it, and so that's where that statement comes from.
That's fair. That's fair. I guess. Okay. Okay. So now we know the world is not classical. That I think that was like disproved in like not around 1920s, maybe earlier, basically when quantum mechanics came about. What if we look at this quantum mechanically? Surely, like, there's probably a more how should I say it? Like a more kind of refined way of looking at entropy from a quantum mechanical point of view.
The situation, unfortunately, actually gets worse once you
Oh,
instill quantum physics. I mean, the contradiction, the conundrum, right?
yeah,
Because
yeah.
because in one of our previous episode, there is this really sacred laws of physics. One of our old episode. It's so sacred that it surpasses conservation of energy, momentum, pretty much any conservation you have, right? And that's the conservation of information, right?
Mm-hmm.
And loosely speaking, it's the conservation of possibilities. That means, hey, if a quantum coin could land face up versus landing face down, even if you observe that it landed face down, this face up possibility still exists somewhere in the universe. That information is not lost, right?
Mm.
Now you ask the question, well, entropy is kind of like counting possibilities. Then you're literally telling me that those possibilities never go away. So it's even
Mm.
saying from a stronger statement that entropy does not change. There just is, all these possibilities is constant over the evolution of the universe. So it's a even more conundrum now. Entropy is even almost kind of like less useful when you look at quantum physics, because there's even
Mm.
more reason why it should stay the same, basically.
Mm. So that makes sense. So you're saying basically that in quantum mechanics, there's preservation information that was actually covered on a previous episode far back. So if y'all are interested, it's in our demystifying quantum mechanics first episode, most sacred laws in physics. Also available on all your podcasting apps if you prefer an audio form. So in that episode, we covered that there's this really sacred law of conservation information, more so than energy, momentum, angular momentum, as you were talking about. And this is basically conservation of like possibilities. So it's not like if I do a measurement or do anything to our universe, the possibilities will be gone. They'll just be somewhere abstractly in the universe that might be highly inaccessible to us. Kind of like,
Mm-hmm.
if you flip a quantum coin, it lands on face down, as you were saying. That possibility of face up is still there, but we can't really, it's difficult for us to access it in some weird way.
Mm-hmm.
Is that, am I understanding that correctly?
Yeah, absolutely. And actually from there, born a kind of more a newer definition of entropy, right? This hiding of information. But
Mm-hmm.
but I mean, going back to your point, yeah. So in some sense, quantum physics is kind of like the most natural way to pixelate your universe, right? Because
Mm-hmm.
when you zoom into quantum particles, they kind of have a finite size. They're not infinitesimally small anymore, and there are some certain limits on how much you can pack in a given volume of space, because of
Mm-hmm.
things like quantum gravity and whatnot. So quantum physics should be the right way to pixelate your universe and to do these possibility counting. But like if you do it, the number of possibilities is conserved. So it's kind of like nature's way to getting back at us again, to be like, you know, you're still getting it wrong, right?
Mm. So actually, I want to ask a question now. Now shifting to this perspective, of entropy as like a measure of our ignorance or uncertainty. If we look at it, we do a experiment on a quantum system. Let's say flipping a quantum coin, and it comes
Mm-hmm.
out like tails or something like that. From our macroscopic point of view, we'll have seen it like, I'm going to use this in quotes because we can have a whole discussion about it. Actually, I'm hesitant to use it, but like the word colloquially collapse in some sense, even though it's not exactly a collapse. Like there's one state that it becomes where it's like it's face down. The number of classically, I would expect number of possibilities to actually go down. So why is it that like, classically we perceive number of possibilities to go up, because we're doing measurements. Classically, I imagine like if I translate it to the language quantum mechanics, classically we're doing these constant measurements just at a macroscopic level. So why is it that like number of possibilities are perceived to be going up rather than down if I measure something?
Yeah. I would say that that's an excellent observation. Um, and and these questions actually cannot fully be addressed just by entropy alone, basically,
Mm-hmm.
right? Um, for for instance, when we go to some of these physics example, like why is it that an ice melt on the table melts, right? And you,
Mm-hmm.
you might say, oh, it's because the air molecules kind of escape. You want to explore more possibilities, and yada yada yada, right? But
Mm-hmm.
but ultimately, the reason why it was even able to explore more possibility was because, well, someone put an ice cube there on the table in the first place, right? Someone kind of arranged a system so that it has the capability to explore more in that way. But it's kind of artificial, right? Because like you kind of have to put an ice cube on table to even start this conversation, right? If you hadn't done that, if you just had air in the room, it wouldn't have happened. So it's a little bit of an artificial consideration, right? And so from that angle, the increase, like why more possibility is explored, it has more to do with, why is the universe set up the way it is to begin with, for such a thing to happen, right? And maybe it's helpful to kind of contemplate the opposite, right? Imagine there were no ice cube. It was just air. Like no one placed an ice cube there to observe it to melt. It was just water vapor, right? Then we wouldn't have this interesting discussion anyway. And imagine applying this to the entire universe. Imagine a universe that was just kind of set up in a way that it's kind of has all the possibilities explored. In a way, it just wouldn't be a very interesting universe, right? Like, not much would happen. So in some sense, kind of like, look, things are happening, but like, come on, you wouldn't be asking this question if things weren't happening, right? So the question is, to what extent is this question a valid question? I don't know if that makes sense, right?
I guess like I want to kind of like I'm thinking how to articulate this. So could we instead like say that we're, if we're just focusing on like just kind of the ice cube by itself, that may not be adequate enough. But if we were to take like a step back and say, okay, there was some process in the universe that took, water and liquid vapor state, and I don't know if I'm using the term, like cooled it down to becoming an ice cube, and that process of cooling it down increased, like loosely speaking, increased our perceived possibilities of the environment as a whole, and that actually what makes entropy go. I don't know. Is that like approximate, or
It's more like the fundamental laws doesn't quite respect the macroscopic constraint we place on the world. Like it's kind of like this pixelated grid that we place, right? If we look at things pixel by pixel, the laws of physics doesn't respect that, and the difference is this level of coarse graining. It turns out that when you coarse grain your physics, you kind of zoom out and kind of sum things up. Like imagine you're on an airplane, right? You're just taking off an airplane, and the buildings look smaller and smaller. The people look smaller and smaller. And if you zoom out really further, you see planets, and if you zoom out even more, you see solar system and galaxies, right? The statement is that as you zoom out, the laws of planets, galaxies, solar system, there's no reason why there needs to be a collusion between these macroscopic laws and microscopic laws. So that's why, like, the microscopic law didn't anticipate there to be a macroscopic universe, right? So there's kind of like a little discrepancy. And that's why as you zoom out, things tend to get a little more scrambled, right? It's almost like you look at the digits of pi. If you just zoom out, you see a million digits, and you just squint really hard, you just see like a random mess. That's kind of what's going on. If you just zoom out in our world, you kind of see more and more of like a random mess. Like the details tend to get washed out. So really, the statement is more about sort of this zooming out property of our universe.
I see. Okay. So what you're talking about is like it's an ill-defined question because it matters how you coarse grain, meaning like what level of granularity you go to. The more granular you go, maybe there are like, I don't know if I want to say there are more possibilities, but I mean, if I take like the pixel example, like as we were talking about earlier, the size of your pixels is a form of coarse graining. Is that correct?
Yeah, exactly. You're kind of placing your system, you're pixelating your system. It is a form of coarse grain. You're kind of ignoring the details and kind of looking at a new system, an emergent system. That's just like, hey, instead of looking at an infinitesimally small dot, I'm just gonna pixelate it more and more. I'm gonna zoom out, right?
Mm.
And that's when the scrambling happens, really. So
I see. I see. So, okay, so I guess like coming back to the original question that we asked at the very beginning of the episode, and we're almost at time, so we may not be able to get into it and maybe save it for future episode if we have more details to cover. But this question of like, oh, why did the universe start off in a low entropy state? Meaning, so my understanding before we talked about any of this was like, oh, the universe was like much smaller, it was more densely packed. So even though you could argue that space itself was confined and then expanded out and stuff, but let's just say like, the area it was confined to was very small, so you know where everything is, and it's like, oh, the entropy must be low because of that. And now, like after the Big Bang, there's this cosmic inflation happening, and even right now, things are getting farther apart. So there's this notion of like, oh, entropy is increasing because the number of possibilities of like where things can be is also increasing. So I'm curious, like looking at it from a cosmic lens, with this new understanding of entropy, how would you explain this to the audience?
yeah, I would just say that this question is kind of borderline, not exactly a question that can be addressed by science anymore, right?
Mhm.
Because first of all, this definition of entropy is ambiguous. When you say entropy is higher in entropy was lower in the beginning of the
Yep.
universe, you
Yep. Yep.
kind of need a coarse graining system, right?
Mhm.
Does it make sense that we coarse grained the universe in the past the same way we coarse grained it today? I'm not sure because the universe has changed a great deal, right? So that's kind of
Mhm.
ill-defined. So the only sense of that question that's kind of left over is that there's this sense of possibility that somehow there were things to explore, right? But then you have to ask
Mhm.
yourself this, right? Like how much exploration is too much, right? Like if the universe had nothing to capable for exploring, it just would have been a very empty universe, boring universe, right? Imagine the universe is just a power of hot plasma, never changing, right?
Mhm.
Then then would you have been asking this question? So so at some point you kind of have to take a stance in science, right? Science is trying to explain something given something else, right? You
Mhm.
give me the initial condition, and science goal is to try to explain what happens after that. I mean, of course, you
Mhm.
can try to keep asking questions, be like, well, why is the initial condition that way? But then again, you can ask this question again. Well, why is the initial condition of the initial condition that way? And it's just never ending, right? I mean, you gotta start from somewhere, right? So I think for a lot of scientists, me and myself included, physicists,
Mhm.
the initial condition of the universe, that's it. We're just given that, right? Like I'm not saying that you shouldn't try to explore it. Sure, go back further, but you have to, like, you're probably gonna see that whatever entropy you define, it's even smaller back then, right? I mean, how small is too small? What's the numerical value that you might be happy or unhappy with, right? It's
Mhm.
completely ill-defined, right? So I would say sometimes these questions don't necessarily deserve an answer because you are using terms that aren't necessarily even all that well defined to begin with. So it's kind of like going in
Mhm.
circles a little bit, right? You're defining things that are not
Mhm.
so you're defining concepts that are not so well defined, and you're using it in such an ill-defined situation, the initial state of the universe. We hardly know what that looks like, and then asking these abstract questions, and now it's like it's no wonder that you can't really have a satisfactory answer, right? I think that would
Mhm.
be my take on it. You know.
Gotcha, gotcha. Okay, so what I'm hearing from this is that it's an ill-defined question, so the question doesn't really make sense because there's a level of like arbitrariness to it.
Yeah, yeah. And I would say because entropy is such a generic concept, it's just counting
Mhm.
possibilities.
Mhm.
We shouldn't be so sidetracked by questions regarding entropy. Like for example, I'll give you the ice cube example. But like, why did the ice cube melt? Some people like to answer it by, oh, because entropy need to increase. But I don't like that answer. Because for many things, entropy will increase depending on how you define it. What's more important is actually the molecular dynamics, right? Literally, water molecule bond to the ice, got jiggled, and then escaped, right? Like that is the right definition. It doesn't. I mean, entropy is kind of like an emergent explanation. It's almost like someone asking, like, "Oh, why is this chemical? Why does this chemical kill people?" And if you answer this by, "Oh, it's poisonous," it doesn't tell you a whole lot, right? It's
Yeah.
like you're just labeling it as poisonous. And entropy is a little bit like that. Maybe not as contrived, but the increase of
Yeah.
entropy is just like, okay, things change, possibility increases, but it doesn't really get into the physics, at least not quite. So that's why I don't really like entropy as an explanation, even though it's reasonable explanation. But deeper explanations usually go beyond entropy, right? You need physics. That's why we study
Yeah.
physics here, right?
Fair, fair, fair. All right. So our audience member has asked us one question, or rather, not a question, but necessarily more would like to see your comment. I think this is when you were talking about a plane going up or maybe an ice cube melting or something like
Mm-hmm.
that. It says, my understanding was that the phase changes were driven entirely by entropy and independent of the atmosphere above it. What is do you have any response or any thoughts about that?
Well, I would say in terms of the phase, yeah, for phase transition, it's a entropy is a clearly decent use, and the reason is because, of course, remember that there's a real physical explanation for things like ice melting, right? You look at the molecules, it moves out, yada yada in certain ways, right? And the reason we resort to entropy is because there's sort of like a universality aspect to it. What I mean is that if you look at the behavior of an ice cube, or I don't know, like or dry ice, right, or solid nitrogen, I guess you don't really get access to that. That's hard, right? Or any kinds of solid, that can melt. You can you of course you can repeat the analysis for different types of molecules. You get a similar conclusion, right? Then of course these specific explanations become less powerful now because you see this general universal behavior. And that's why entropy can come in and be like, hey, look, the reason why these are so similar because there's this emergent statistical property that they all seem to conform. So now this is where entropy really derives its power. It's almost like a common ground that that all these specific properties rely on. And so that's why it's a good explanation. Like there's only is a problem when you try to go backward, right? You're trying to say, oh, because of entropy, this and that. Well, let me use entropy to dig at the fundamental laws. You can't really do that. Entropy is about common ground of a broad class of materials, about things that has some sort of universal behavior, and that's that's what it is really used for, right? You talk about many things at the same time.
Gotcha. That makes sense. Actually, one question that I have, which maybe getting us on a tangent, and feel free, we can defer it for later if it's too much. But like the concept of like virtual particles and quantum mechanics popping in and out of existence, like how come that doesn't change the entropy, or why does that not have any impact on that?
Actually, it does.
Oh,
And maybe that's a story for a different time. I mean,
okay.
we have not covered what entropy really is in a quantum mechanical sense, and the greatest application is black holes. So but let me just give a quick spiel and we can end it, right? So we know that
Yeah.
quantum physics preserve possibilities. So how come you can reasonably count possibilities if there's only one, right? Because it's conserved. The way we do in quantum physics is we look at if we ignore certain parts of the system to see what the apparent possibilities are, because you can only reconstruct all the possibility if you have information about the entire universe, right? But if you hide certain parts of it, it would appear that things look kind of random. And for example, that happens in black holes because you cannot see the inside of the black hole. But quantum physics clearly has information about the black hole. But if you hide the inside of the black hole, it would look like there are random possibilities appearing. And that's why black holes have entropy. Right? But that's for discussion for a different time. And if you look at Hawking radiation, that could be interpreted as due to virtual particles. So in some ways, yes, virtual particles do contribute to entropy. But this is, now we're talking about like a way more modern understanding of this concept of entropy, which is still being studied. But let's not go there.
Yeah, that's fair.
Next
That's
time.
fair.
Yeah.
Okay. Yes. I was just wanted to scratch the curiosity itch that I was feeling on that one. All right then. Well, anything you want to leave our audience with before we head out?
Yeah, and I hope people don't get the sense that I'm trying to diss entropy, but I truly believe that there just is too much talk about entropy, right? Entropy
Mm-hmm.
is like a nice hint of something interesting, right? But it's
Mm-hmm.
not the ultimate thing, right? It's a general
Mm-hmm.
principle, but not a specific principle, right? So I would say please use entropy responsibly. It's not disorder. Let's get that out of the way. It has to do with information, has to do with our ignorance, has to do with coarse graining our system, and it's a tool to showcase interesting bits about the universe to us. But ultimately, what's important is physics, right? And that's what we should focus on, like deep physics, not just entropy.
Yeah, that's a wonderful thing. Please use it responsibly.
Use responsibly, entropy.
Yeah. Yeah, I could imagine that as like an alcoholic beverage. And yeah, anyway, that's yeah, before I go down that train of thought. I want to thank everybody for joining us, and we'll see you all next week.
Yeah, see you all next week.
Yep.
Bye.
Bye. Oh, Tim, one of our audience members is asking for the Discord.
Oh.
So if you can post